Hello everyone, welcome back to this series of videos. In this video we are going to complete the paper. We are going to read till the end because there is no that much implementation and that much question in here to be answered by the code. But after we finished it, we are going to create this architecture that was introduced in figure 1 to do what we wanted. So as you can see in here, we just needed to create this multi-head attention, which was the base and most important thing in here. The another part that is important is positional coding. The other parts are not what we are going to implement because the libraries and the frameworks that we are using, which are TensorFlow and Pytorch, have feed-forward neural networks. They had added normalization and all of these things. They had software, they had linear layers. So this is not that much hard. So our plan is to finish this paper in this section, and then in the next session we are going to complete our code both in TensorFlow and Pytorch and finish this series of videos. Now we are going to talk about the applications of attention in our model. The transformer uses multi-head attention in 3 different ways. What are the ways? It is encoder attention. What does it mean, encoder attention layers? The queries come from the previous decoder layer, and the memory keys and values come from the output of the encoder. This allows every position in the decoder to attend over all positions in the input sequence. This mimics the typical encoder-decoder attention mechanism in sequence-to-sequence models. Let's talk about this thing. Okay, it says that they have something called encoder-decoder attention, which in that the queries comes from the previous decoder layer. And the memory keys comes from the encoder. So, what does it mean? Let's see this. It's a previous decoder thing. So, previous decoder thing. Consider that we have this encoder. 2 things are coming in here, which are what? Okay, we know that these are the queries and values. And this is the queries that are coming from the previous decoder. So this is basically saying that. So they have encoder-decoder attention, which uses what? Queries from the previous decoder layer and keys and values from the output of the encoder. This allows every position in the decoder to attend over all positions in the input sequence. This mimics a typical encoder-decoder attention mechanism in sequence-to-sequence model. It's basically saying in here that, let's talk about this in here. Consider this example. We know that we have an input sentence and we're going to create an output. After the encoder, we have queries and we have values and keys from the encoder, and we are going to find the best next word in mass language modeling of our transformer architecture. So what we need to do is that to use queries to check whether what is the best word to be put in the mask token for this sentence. So we need to see the keys and values from the encoder, and the query that we want to find out is basically based on the decoder. So it's how it is happening in here. The next use or different way they are using multi-head attention is this. The encoder contains self-attention layers. In self-attention layer, all of the keys, values, and queries come from the same place. In this case, out of the previous layer in the encoder. Each position in the encoder can attend to all positions in the previous layer of the encoder. Similarly, self-attention layers in the decoder's allow position and the decoder to attend all positions in the decoder up to including that position, which is a mask token. We need to prevent the left-forward information. So they are preventing left-forward information because we are not going to see information from the left. We are going to complete the sentence. Saying a word that is after that mask token is not a good thing for us. For example, if I'm saying that Cristiano Ronaldo is the best mask token in the football, so saying that football may help you, or the best something in football is Cristiano Ronaldo. So to find that something that I said, which was a mask token, saying that Cristiano Ronaldo and that football can help us to find the best solution, but we are not going to see something like that. We are find and increase the language model in here, or increase the knowledge of language model is better to say. So they are going to prevent left-forward information. Because of that, they are using that masking technique, which we need to where am I? I'm teleported to somewhere else, and they need to use that masking technique, which puts minus infinity for all values which are after the mask thing, which means that they're not important for us, so we should not pay attention. This section was talking about the architecture. Basically, if you look at here, we can see that we have a attention here, we have multi-attention. This was that. If I'm going to show you, let me do this. Okay, we are going to talk about this, and this. So this was that encoder, decoder, attention. This was that masked attention in decoder, and this is the attention in encoder. So that's it. It's not that much hard, is it? Let's continue the paper. Then we are going to talk about position-wise feed-forward networks. What is position-wise feed-forward? We know that what are feed-forward networks, but we don't know what does it mean to say position-wise feed-forward networks. In addition to attention sublayers, each of layer of our encoder and decoder contains a fully connected feed-forward networks, which we saw that in the architecture as well, which is applied to each position separately and identically. So it is applied for each position separately and identically. This consists of two linear transformations with a relo activation in between, which seems that it's not something that much hard. We are just going to use two linear transformations with a relo activation function. That's not something hard. So we know that relo activation functions returns the value or returns x if the x is greater than 0 and 0 if x is less than 0. So we are doing this. This max of something is the relu function. This is the first linear layer, and this is the second linear layer. So we have a feed-forward neural network with two layers. The first layer activation function is the relu, and the next one, it seems that it does not have any activation function because we are not using that max function in here, which means that we are not paying attention to activating the value of this layer. So I made a mistake. I had to use this rectangle. So that was it. While linear transformations are the same across different positions, they use different parameters from layer to layer. So it is what's happening in the neural networks, isn't it? Another way of describing this is as two convolutions with kernel size 1. The dimensionality of input and output is the model equal to 512, and the inner layer has dimensionality of 2048. So we have inner layer dimensionality and inputs and outputs. So we have some idea about it. Also, it shows that y birth is given. It gives us a vector of 512 somehow. So that was it. Now let's talk about embeddings and softmax. Similar to other sequence transduction models, we are talking about sequence, we used learned embeddings to convert the input into tokens and output tokens. The tokens to vectors of dimension d. Let's put this come to here. Okay. We also use the usual learned linear transformation and softmax function to convert the decoder output to predicted next token probabilities. In our model, we share the same weight matrix between two embedding layers and the pre-softmax linear transformation similar to this paper. In the embedding layers, we multiply those weights by this. Actually, what's happening in here is not that much hard or something very phenomenal. What are they saying is that, okay, we are talking about embeddings. So this embeddings means that we should pass, you know, we know that when we have a sequence of words, which is a sentence, converting this sentence to something that the computer can see it and can understand it, we should make a vector of that. Although we can use other things, but the base thing is creating a vector. Which embedding that you're using, it's Word2Vec, it's Club, or other things, it doesn't matter, but you're using a vectorizing to create embeddings. And embeddings are what we are using for words, which are in the inputs and outputs. The words are tokens, basically, somehow. Although, for example, some punctuations are not words, but they are tokens. But in general, we can say that words are equal to tokens somehow. And it's saying that while you're using softmax because they want to predict the next word, as I mentioned, I think in the first session of our videos, how we are going to predict this. It is happening like a large softmax because consider that we know something, we have some information about the previous words and which are created by attention and that fits for neural network. But the thing that is happening in here is that we are going to say what is the mask token, how we are going to predict that we have a variety of words, which is a lot of words. We can say that is n words that we have seen in our corpus, and we are going to say which word is the best. So it's a large softmax, and they are saying that they are using softmax to find the best word for that masked token. The next thing is positional coding, which is one of the most important things in here. As I mentioned in the first video, finding that in recurrent neural networks, each word is passed after another, so we are seeing the sequence. But in here, as we are going to pass all the words into a network, so we do not see the sequence in here. How we are going to create that sequence? We should encode something about their position and their index in there. One way is to use um, the index of the word. For example, the first word is 0, the next word is 1, until the end word. But the thing that is happening here is that when the sentence is very big, we have large values for indices, and this makes some problem for us, as um, passing these large values to network may cause some problems for us. We know that large values and some small values are not good for the neural network to learn them. It makes the neural network working bad and not learn the things that are happening in our data. So to prevent this, we can use uh, another type of encoding, something like um, we can say something like one-hot encoding that we had for the outputs in machine learning models. The positional encoding is something like that. Okay, so it's saying that since our model contains no recurrence and no convolution, in order for the model to make use of order of sequence, we must inject some information about relative and absolute position of them. How we are going to do that? Uh, It is positional encoding. The input encoding and the bottom of the encoder and decoder stacks. The positional encoding, you have the dimensional D model as embedding so that can be summed. There are many choices of positional encodings, but what they are using in here is sine and cosine functions in here to create those positional encodings. Which are described in here. Using these sine and cosine values creates the positions uh, very well for us. Let me show you something in here. If we are going to talk about encoding, um, positional encoding, better to say, in here, um, you can see different images in here. So using sine and cosine functions uh, helps you to encode the values. As you can see, this lowering is showing us that how this you know positional encoding technique works, because it's getting less and less when we go further in our sentence. So this is exactly what we want for our encoding. There are a bunch of readings. I suggest you to read this article in Machine Learning Mastery blog, which talks about positional encoding, which is one of the best uh, description of this thing. But just consider that as create a vector for us, and we can encode this vector in our embeddings to have some information about the positions. We are going to implement that, but for the basic thing, you can read that article as well. Now it's saying that why they're using self-attention. In this section, we compare various aspects of self-attention layers to the recurrent and convolutional layers commonly used for mapping one variable length sequence of simple representations to another sequence of equal lengths, such as hidden layer in a typical sequence transduction encoder or decoder. Motivating our use of self-attention, we consider three uh, criteria. One is the total computational complexity per layer. Another is amount of computation that can be parallelized as measured by the minimum number of sequential operations required. And the third is the path links between long-range dependencies in the network. So why they're using self-attention? There are three reasons. One of them is this: total computational complexity per layer. The next one is the amount of computation that can be parallelized. And the third one is the path lengths between two long-range dependencies. And then learning long-range dependencies is a key challenge in many sequence transduction tasks. One key factor affecting the ability to learn such dependencies is the length of the path forward and backward signals have to traverse in the network. The shorter these paths between any combination of positions in the input and output sequences, the easier it is to learn a long-range dependencies. Hence, we also compare the maximum path lengths between any two input and output positions in networks composed of the different layer types. So it's not something that much important. As noted in table 1, self-attention layer connects all positions with a constant number of sequentially executed operations, whereas in neural recurrent layer requires n sequential operations. In terms of computational complexity, self-attention layers are faster than recurrent layers when the sequence length n is smaller than the representation dimensionality d, which is the most often the case with sentence representations used by state-of-the-art models in machine translation, such as word piece and byte pair representations. To improve computational performance for tasks involving very long sequences, self-attention could be restricted to considering only a neighborhood of size r in the input. So its complexity can be reduced to this thing. So it's talking about that thing. Let me talk about, instead of reading these texts, talk about this complexity that we have here. Okay, so if we are talking about convolutional layers, we are talking about recurrent layers, and self-attention with restriction. As we can see in here, we can say the convolutional is the worst one in complexity per layer, but about the self-attention and recurrent, we're talking about the dimensionality and the length of the sentence, and in which way they are better than another one. But if we do not consider the complexity per layer, if we are talking about the sequential operations, we know that the sequential operations here is O1 because we are just multiplying matrices to each other. But in here, we are saying each word and then another word and then another word. So it's different. In convolution, again, we do not have that sequence. So it's O1, and in self-attention restricted one is also O1. The maximum path length also in here is O1 because we are seeing all the words together. But in convolutional, no, it's not happening like that. As we are making a convolution, we are going to have a window size of k. We are saying that those k window sizes. So although we are not saying one word after each other, but we are saying k words, okay, window size of k after each other, so it's log k of n. In the restricted one, we are restricted one. We are doing that, but with it's somehow it's like recurrent neural networks, but we are doing some of them parallelized, so it's O(n) divided by R. But in self-attention is O(1) because we are seeing all the ports together, and so the maximum path length is not that much important for us, as we are seeing all the ports together. So based on these things, we can say the complexity per layer can be what? So these are the complexities. As you can see, these two things can make some questions for us. It's not easy to say which one is better in terms of complexity per layer because it depends on the dimensionality and n, but as it's mentioned in here, the d is not that much important for us. So usually n is smaller than the representation dimensionality. So as n is less than dimensionality, we can say that self-attention is doing the best. Or if r is less than n, self-attention restricted one is the best. But in general, we can say that self-attention in terms of complexity and the number of operations, the maximum things is the best thing between these different operations. In addition to recurrent neural networks, we have convolutional networks that are doing somehow good, but the problem with them is that convolutional neural networks cannot find the, you know, they, as attention is finding how much of word is related to another word, but calculate a number of that. Convolutional networks are not doing that, and as it's important to have this information when talking about a sentence. So convolutional networks, although they are somehow better than recurrent neural networks in terms of complexity, but they are not good in terms of performance. And it's better to say that self-attention networks and transformer architecture is better than recurrent neural networks to see that. And here is they're talking about how they were doing that, the tasks that we talked about. In there, we are not going through these things and how they were trained their model, then what was the hyperparameters. You can read them by yourself and understand them. So there's nothing important in here. We talked about how this model is good, and you are saying that if you're working in the area of natural language processing, you can see that transformer architecture is the best architecture out there. They are creating state-of-the-art models, state-of-the-art language models that are helping to improve the performance of artificial intelligence models in different tasks, such as translation or sentiment analysis or other things that are very useful out there. So this is what's happening there. I'm not going to talk about this thing. Also, they have their code available based on TensorFlow. You can see their code as well, but I'm going to implement it myself because not only I think I can, you know, learn something for myself, teach you something that how you can code that, but I think that by coding you can see how these things that we talked in here are working exactly. So that was it for this session. In the next session we are going to complete our codes in both TensorFlow and Pytorch, and I see you in the next video. Till then, stay safe.